Thanks, Tommy. And thanks everyone to attend session 4. It's called Big Data Analytics for Structural Health Monitoring. But I feel that both presentations, it so happened that they all coming from Griffith University. And they sort of flow well from the previous session 3, non-destructive techniques. I feel that they both related to that area. But anyway, so the first presenter will be Thomas Sharry. He's our PhD student working, in collaboration with colleagues in Vietnam, and we're looking at a bridge, a cable city bridge over the Saigon River in Ho Chi Minh City in Vietnam, and we use the on-site sensor data to conduct some model updating work. So without further ado, I will hand over to Thomas.
Thank you, Hoang. I'll just share my screen here. Okay. Good morning, everyone, or good afternoon, and thank you to Professor Guan and the organisers for this opportunity to present to you all some of the work I've been doing as part of my PhD candidature at Griffith University. So I'll be presenting today the progress so far regarding the finite element modelling and model updating of the Phu cable-stayed bridge in Vietnam. So I just want to acknowledge our research team, my supervisors, Professor Guan and Associate Professor Erwin from Griffith University, Associate Professor Nam Hong from Ho Chi Minh City University of Technology, and Dr. Andy Nguyen from the University of Southern Queensland. So I'll give an overview of the Phu Bridge and details of how the initial model was developed with some initial results, then on to results from the ANSHM data through operational model. Someone's muted me there. I assume, can you hear me all?
Yes.
Yes, Thomas.
You can, okay. Parameter sensitivity, and then onto the model updating procedure that will be used. So the Phu Bridge is a cable-stayed bridge in Vietnam over the Saigon River in Ho Chi Minh City, connecting District 7 on the southwestern side to District 2 on the northeastern side. A reinforced concrete, 380-metre main span. The bridge was opened to traffic September 2009, and the ANSHM system was installed towards the end of 2019. And that system comprises 3 inclinometers on the eastern side pylon, 8 accelerometers, so 4 on the deck, these light blue dots here, and then another 4 on the cables, the 4 longest cables on the eastern side of the bridge. 6 cameras, 1 weather station, and 1 anemometer. So considering the fact that the ANSHM system is relatively new, and because the number and locations of the sensors are limited, a model-based approach was proposed to create a finite element model of the bridge that would be used to complement the ANSHM system for identifying global structural behaviour and to be used as a baseline reference for condition assessment. So the first step was to identify different cable-stayed bridge modelling approaches that exist in the literature. So just a very brief overview of these. A single girder model, which represents the deck as a line beam element, double girder model, triple girder model, and a multi-scale model using a combination of line and shell or solid elements. And from the literature, by far the most common was the single girder model, also referred to as the fishbone or spine beam model, mainly due to the accuracy or the simplicity in modeling, first of all, and the accuracy in identifying global properties. For modeling the stay cables, 3 main approaches, the linear model, So a node at the deck level, a node at the pylon, straight line element connecting the two, adopting the cable's modulus of elasticity, so it ignores geometric effects. An improvement on this, or a refinement, very similar but uses an equivalent elastic modulus using the Ernst formula here, which approximates the cable profile as a parabola, and then a multi-element model, so a number of intermediate nodes connected with straight line elements, the weight distributed along these nodes, so this is thought to better approximate the cable profile as its true catenary shape. And just an example of the difference between one element cable system and the multi-element cable system. One element cables results in global behavior, so behavior in the deck and the pylons, whereas multi-element cables will result in local behavior, so individual cable vibrations. So a glance at the literature shows that the equivalent elastic modulus for the one element cable system is by far the most popular. And there are also many studies with multi-element cables, mainly for investigations into the interaction between local and global vibrations. So the next step then was to, with that information, the next step was to duplicate an existing model in the literature to identify a valid method or approach that would be used to model the Fermi bridge. So a paper by Li et al. 2014 models a cable-stayed bridge in China, which is used for ANSHM benchmarking studies. So that model is presented here on the left-hand side of each of these figures, along with the identified natural frequencies also on the left here for the first 6 vertical modes. You can see the model approach used was the single girder method and one element cables. And then my attempt at duplicating that presented here on the right using Abacus. As you can see, fairly consistent in terms of mode shapes and also with the natural frequencies. One model was a little bit stiffer, so there's a little bit difference in the frequencies there, but consistent overall. So a worthwhile exercise in not only for practice, but identifying a valid approach for modeling Fermi. So the bridge dimensions are available in 2 publications, and then from the model in Abacus, 20 parameters needed to be defined related to the geometry of the bridge, the non-structural girder mass, and then material properties, concrete strength, density, etc. So all that needed to be defined. And from there, the initial model of the Fermi bridge was created. So again, a comparison with the literature using similar sized bridges and their FE models. The number of elements range from roughly 600 upwards of 3,000. So my initial first model had 462 elements. Those elements were slowly increased until convergence in results was achieved with the model with roughly 2,434 elements. And just an example there of how convergence was achieved in the results for mode 1 as the number of elements increased in the model. This is a mode shapes. This is the first mode 1 symmetrical vertical mode. A lateral mode and a torsional mode. Okay, so that was the initial model and its initial results. So moving on to the SHM data. So just a very brief overview of with model identification as the goal here can be achieved through operational model analysis or experimental model analysis and different vibration inputs there. So obviously for long-term monitoring, we're interested in ambient vibration, which can be expressed in either the time domain or the frequency domain, examples of those. And then within each domain, a set of methods and sub-methods used to identify the modal properties from that data. So for my project, I'm using a program called Artemis Modal Pro, which allows users to select either the stochastic subspace identification method or the frequency domain decomposition method, depending on which domain they're working in. So this here is a 1 hour time series data, just an example from the Fermi bridge. So the mid-span accelerometer in the X and Y direction, and the side-span accelerometer in the X and Y direction as well. So the initial data looked at over a 1 week period, which was 168 1-hour sets of data were analysed. And it's an example of here, after converting to the frequency domain. So it's a lot more intuitive. You can see the prominent peaks there. So using the frequency domain decomposition, essentially a peak picking type method, the natural frequencies and the mode shapes were identified from the data of the bridge. So just some mode shape animations from Artemis. You can see the first vertical mode there. So on the left-hand side is the mid-span of the bridge, and the right-hand side the side span. And each of these arrows here is the location of an accelerometer in the X or Y direction. So the second asymmetrical vertical mode, lateral mode, and just an example of a higher lateral sway mode there. So that data was from the end of July and early August. So we have the initial model results here. We have the range of data, ANSHM data, the frequencies that were identified from that, their mean values, standard deviations, and then the percentage difference. So the difference between the initial model and the mean values from the data. As you can see, in some cases, the model underestimated the natural frequencies, in some cases overestimated as well. So comparing that to what's in the literature, you can see before model updating, minimum or maximum differences, absolute differences range from between roughly 6% and 41%. So for my results, having a maximum value of 10% puts me down at the lower end of this range, which is a good start. And then after model updating, you can see I'd expect a maximum difference of ideally less than 6 or 5%, which would be a good achievement. So moving on to parameter sensitivity. So the absolute sensitivity was calculated for each of the input parameters in Abacus, simply by the change in response divided by the change in parameter value. It's just a very sort of bird's eye view of the different sensitivities. Cable cross-sectional area is by far the most sensitive, so I've had to separate it from the rest. And you can see the next sensitive would be the girder cross-sectional area. You can see how it changes as well, sensitivity for each mode, 1 to 15. So another way to look at that data is to break it up by mode. And we can see now how individual parameters, or how sensitive they are for each mode. So for the early modes, for example, the pylon side area is quite prominent. And then in the higher modes, the pylon upper leg area comes into play as well. So it just gives you an idea of, or a better feel for how the model responds to different changes in parameters. So the parameters were then rearranged from most sensitive to least sensitive, cross-sectional area being the most sensitive, followed by the girder cross-sectional area and pylon dimensions. And you can see things like Poisson's ratio and the NPA dimensions had very little or no sensitivity. So manual tuning was attempted just to see if that initial model could be improved. So the two most uncertain parameters were the girder cross-sectional area and the moment of inertia. So those were slowly increased over a number of iterations. The red here indicating a mode getting worse, whereas the green showing improvement. So by the third iteration, small improvement across most of the modes. You can see mode 1 and 2, they're worsening. And this mode 6 here was quite problematic, because as you can see, any attempt to improve this mode actually makes mode 1 and 2 worse, and vice versa. Attempting to improve these makes the other modes worse as well. So a good candidate for an optimization type problem, especially when you're including other parameters through model updating. So on model updating, again, a very brief overview of the different techniques or methods that are available. Direct methods, updating the mass and stiffness matrices directly. So obvious disadvantages of that have limited its application to fairly simple structures there. You can see boxes and beams. Sensitivity methods, by far the most popular, iteratively changing the most sensitive parameters. Plenty of applications to cable-supported bridges. The response surface method, using a surrogate model in lieu of the original FE model. Bayesian methods, which consider or use probability distributions of data to better account for uncertainties and variability using Bayes' theorem, and then computational intelligence methods which use high-level optimization methods to solve the updating problem. So for my project, I proposed to use a sensitivity-based model updating with constraints. So the relationship can be posed as an inverse problem. I'll run through this very quickly because I'm running out of time. So using this objective function, it introduces a couple of weighting matrices which take into account the uncertainties of the measurements and the parameters. Constraints, so making sure that the changes are physically sensible. So constraints are placed on the change in parameters. And then that can be expressed as what's called a quadratic programming problem, comprised of either vectors or matrices with some of the terms that we're familiar with, changes in the parameter, changes in the natural frequencies, etc., the sensitivity matrix. So a very brief overview of that, defining those inputs, initial parameters into the model, initial frequencies, comparing it to the RMA data. If there's a difference, computing the sensitivity, defining the constraints, solving the optimization problem to determine delta P, the change in parameters, which are then added on to the initial parameters, and a new iteration is then starts again. So that's currently what I'm working on, a MATLAB script to automate as much of this as possible. And then for continuing research, I'll also be considering different modeling approaches, how they affect or identifying the initial results. Considering uncertainties is a big one as well. So data during different periods of or different times of the year, and then eventually using an updated model to evaluate a critical component of the bridge. So using multi-element cable system, if we're able to identify frequencies of the cables, how accurate is that, and ultimately how useful is that in identifying or monitoring cable tension. Thank you.
Thanks, Thomas, for your presentation. And my apologies again for looking at the wrong clock. So mindful about time, so maybe we could have one question, please, from the audience.
I have one question.
Yes.
Yes, please.
Thank you so much, Thomas. It's so comprehensive presentation. I really enjoyed it. I just have one question regarding parameter selection. Did you consider any parameter about boundary conditions, or they are just material and geometry?
Yeah, it's a good question. So the boundary conditions, so the bearings were represented by springs in Apicus. And so the stiffness of the springs was one of the parameters that was looked at, but it turned out to be not very sensitive. In terms of the degrees of freedom, that was a little bit tricky because there wasn't a lot of information in the literature. It wasn't very clear about how other people modeled their bridges in terms of boundary conditions. So really that was sort of just an iterative process of me experimenting with different degrees of freedom and what gave sensible results. So in terms of the spring stiffness, the bearing stiffness, that was included in the parameters, but the degrees of freedom, I just chose degrees of freedom, defined the degrees of freedom, what gave us sensible results, and moved it from there. So that wasn't included in the sensitivity analysis. Does that answer your question?
Yeah, thank you.
Okay.
Okay, thank you. So yeah, because of the time, thank you, Thomas.